Now let's look at the 4 pillars of autonomy. Let's start with the perception module. Perception module includes sensor technologies, which can either be based on visual module or it can be based on acoustic module. These technologies allow the AUV to collect data from its environment and as well as detect obstacles in its vicinity and classify them. The AUV will also be able to map its surrounding using the perception module. Moving on, we have the planning and obstacle avoidance module. The data that is collected from the perception module is used by the AUV to plan its path to go from a start location to a desired goal location while avoiding the obstacles in its path. This is the main job of the planning algorithm modules. Depending on the data that is collected by the perception module, the AUV might need to make some real-time adjustments to its path. This will allow the AUV to safely navigate in its complex environments. Moving on, we have the navigation, localization and SLAM module. The goal of the navigation module is to allow the AUV to localize itself in its environment with respect to a global reference frame. From the planning module, the AUV knows its path from a start location to a goal location. But in order to traverse this path successfully, the AUV needs to know its own location at every point in time. The navigation module uses various localization algorithms in order to give this estimate of the AUV's position. In case of underwater vehicles specifically, due to absence of any global reference frame or global reference measurements such as the GPS measurements, the AUV needs to collect data from its surrounding as well as simultaneously localize itself. This technique is known as SLAM, which stands for simultaneous localization and mapping. Moving on, we have the control systems module. The job of the control system module is to take the AUV's current location and check the error between the current location and the desired location as per the planning module. Using this error, the AUV will generate control commands which will make it move from its current position to a desired goal location. This process of providing the actuation commands based on the error is known as the control mechanism. An AUV might have some thrusters or rudder to be controlled, and it basically goes through a feedback control loop which we will be discussing later down the slides. Implementing a stable control will allow the AUV to precisely complete its autonomous operations. Now let's look at the perception and sensor fusion module in a bit more detail. As we discussed, we have camera sensors as well as sonar sensors. For the camera sensors, we have data being collected in the visual mode. In case of any autonomous system, visual data is a very important thing. But in case of underwater vehicles, staying limited and using only the visual mode is not sufficient. This is due to the attenuation of electromagnetic waves in the underwater region. As opposed to this, sound waves or acoustic mode can propagate up to longer distances without much attenuation, which is why in case of underwater vehicles, acoustic sensing is a more desired way of perceiving the environment. These are the key strengths of sonar sensors. A typical map of a sonar sensor is shown in this diagram here. Depending on the requirement of various missions, there can be various mission-specific sensors as well, such as chemical sensors. These sensors will allow the AUV to detect some chemical signatures or detect chemical compositions of the oceans. Similarly, for various oceanographic surveys, we have sensors such as CTD and ADCP. Having collected all of this data, a perception module can perform sensor fusion algorithms to combine this data and get a better estimate of the AUV's surrounding. Moving on, let's look at the navigation, localization and SLAM module. The goal of the navigation module is to essentially find the position of the AUV with respect to a global reference frame. Consider the AUV as shown here. The AUV needs to locate itself with respect to this global reference frame. It needs to know its x, y, z position coordinates as well as its orientation, which can either be expressed in the form of phi, theta, psi, which are the Euler angles, or it can even be expressed in terms of quaternions. These are the key states that an AUV needs to estimate to know its present state. In case of implementations of control systems, having velocity information is also very essential. The key challenges in AUV navigation are the fact that there is no sensor that is easily available which can give the AUV's global reference position very easily. Since GPS is not accessible in underwater regions, we have to rely on different sensors and combine their information and to get a better estimate of the AUV's position. Here are some sensors listed down which are commonly used in AUVs. One of them is the IMU sensor. An IMU sensor will allow the AUV to get its orientation as well as linear accelerations, along with that the angular rates. There are also depth sensors which will allow the AUV to localize itself with respect to a bottom, with either using a pressure based sensor or using acoustic based. Since the IMU measures the linear accelerations and these measurements are quite noisy, we can't use double integration of these linear accelerations to get the position estimate directly. So, an AUV will typically use a Doppler velocity log, which is a sensor that essentially gives the velocity estimates based on the bottom tracking. This is more stable and can be integrated to give our position estimates in a more reliable manner. Along with that, an AUV can also use sonar and camera sensors for looking at objects in its vicinity and using that information to localize itself. This will typically be present in SLAM modules or simultaneous localization and mapping modules and are content for a higher and challenging area of research. There are various data fusion algorithms such as the Kalman filter, the extended Kalman filter, which is the non-linear version of the Kalman filter algorithm, and a more generalized variant of it, also known as the particle filter, which doesn't restrict the underlying distribution of the data to be present in any specific probability mode. So these are the key ideas behind the navigation localization and SLAM module. In a typical implementation, you can consider various ROS packages such as the robot localization package to implement these algorithms. And they are a good starting point for anyone who is new at robotics.